for the next session. It's a pleasure to welcome Filip Wurdarski, who's going to tell us about application-specific annealers, a case study of the Fermi-Hubbard Annealers.
Thank you. So today I will tell you about some, I would say, different paradigm of approaching annealing stuff, and we'll focus mainly on Fermi-Hubbard Annealers. And this is based on this work that has been done with USRA, NASA, Champaign, UCL, University of Toronto, and UNML. Quite collaborative work, and it's more like a proposal work that we are exploring some completely uncharted territories of annealing and trying to pitch some ideas of building new novel annealers. So this is the outlook of my presentation. I will first focus on the motivation why we are trying to pitch this idea of these application-specific annealers and why we are interested in Fermi-Hubbard models. So I will introduce Fermi-Hubbard models and what are the Fermi to qubit mappings in order to properly implement this on a hardware or on a future iteration of hardware. Then I will focus on what sort of annealing protocols we can exploit and how they can be beneficial for observing something, which will be supported by the numerical results in other section, and then I will say something about a rough comparison between how gate models are trying to solve Fermi-Hubbard models, what sort of resources they require in the near term, and finally what are the experimental perspectives, like what might be done in the future to achieve that, and finally I will conclude my presentation. So yeah, the main motivation is that if you take the definition of quantum annealing that aims to solve first classical optimization problems. So why we are interested in classical, because we have D-Wave. This is me jumping next to D-Wave at NASA. D-Wave solves easing or qubit problems that maybe is not the most general quantum, it's a classical problem, but exploits some quantum effects and tries to arrive to some better results. Optimization means that we end up in the ground or close to the end of the ground state. And problems means that we have some problem, and the hard may be possibly problem, and we try to map this to a Ising Hamiltonian or a quantum Hamiltonian. And there are plenty of wonderful results ranging from machine learning, traffic optimization, phase transitions, all this stuff. However, it's still unknown that if we have only this sort of paradigm, we can definitely achieve quantum speedups. So the question here is what needs to be done to maybe arrive to something that is easier for observing quantum advantage, and which means that, okay, so maybe we need to relax classicality of our problem Hamiltonian, which already brings next level of complexity to the implementation of that problems related to readout, evolution, and so on. So then, if we relax classicality of the final Hamiltonian, of the problem Hamiltonian, what sort of problems can we target there? And then the question is it super complicated to implement? Is it easy, or maybe it's not even worth pursuing this because quantum computers, gate-based computers will always be better there. So this is also an interesting problem. And then what sort of architecture we will need for that? So what sort of components, hardware components, will be required to solve these promising problems? And this is the reason why we are trying to focus on Fermi-Hubbard models, which are proxy models for different applications in material science, in modeling superconductivity, and so on, and quite relevant and also very hard to simulate classically. So Fermi-Hubbard models are given by this Hamiltonian composed of Fermionic operators, collision annihilation operators, and we've got hopping between sites and on-site interactions. And in this work, we are also exploring spinless models, kind of tight binding models. where each side can be either occupied by a spin-up or spin-down particle that is a fermionic particle. Yeah, so like we've got already some sort of mathematical framework of commutation relationships that need to be satisfied there. And in a standard quantum computers, you do not implement fermionic operators. So in order to make this possible, we'll need to employ some sort of fermion to qubit mappings. So like our creation and annihilation operators will be mapped to some Pauli strings, let's say, and these Pauli strings will be constrained by the commutation relationship and the statistics of fermions. So like this is the least, probably not exhaustive list of fermion to qubit mappings. All of them have some nice properties, but also caveats and fairness of implementing. And arguably the most popular one is Jordan-Wigner transformation, where we map fermionic modes to qubit modes. Each fermionic mode is mapped to a qubit. 0 state represents that there is no occupation of a particle. 1 says that there is a fermionic particle. All others are implementing more qubits, so like we have some redundancy there, but on the other hand, they are exploiting the fact that we are not implementing very long Pauli chains, but some shorter Pauli chains. And I would say that when this paper appeared, like that was super promising for us, because we identified that this is novel encoding that requires only Pauli weight free. So like interaction is composed only up to 3 Pauli operators, which possibly could be implemented in near future. So like we ask ourselves question, what sort of requirements on hardware level will be necessary to encode Fermi-Hubbard models within this encoding, and can it be beneficial for annealing scenarios? So for the rest of my talk, I will focus on that encoding, and this is a brief recap of that encoding. That if we got this Fermi-Hubbard lattice, let's say square or rectangular lattice, you can encode this by taking our edges and making them directional, and additionally giving extra qubits. So every other phase has an extra auxiliary qubit that will mediate the fermionic commutation relationship. And with each edge and each vertex, you will associate a Pauli string up to Pauli weight free, so like x, y, x, and so on, where this first qubit will be all living on one of these auxiliary qubits, while the vertices will be simply local Z operators. So if you look at the Fermi-Hubbard model, we have these sort of terms that will translate into this combination of edge and vertices, and finally they will translate into some sort of Pauli strings of this form. So like x, x, y, 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 yeah? Maybe, yeah, so let's go maybe here to the example. So if we got only like a single plaquette of that, our Hamiltonian is given by that. So you see that the interaction between qubit 1 and 2 will be given by this like xx plus yy interaction, and then y living on this auxiliary qubit. If this is this empty phase without the auxiliary qubit, the Pauli weight will be simply 2. But since we are introducing extra qubit, it means that our Hilbert space is larger than the previous in fermionic system. So like we have larger Hilbert space, but our problem needs to be somehow encoded in a logical space. And fortunately with this encoding, we've got the stabilizer formalism that is defined by these stabilizers that are of Pauli weight 8, and they are defining how to restore a logical state from this physical larger space with some extra constraints on how to construct the stabilizers. So there is also some additional knowledge of notion of error correction, like a single qubit error correction here, that might be beneficial for our purposes.
Hang on a sec. Can
Yes.
you just, if I is your sum variable from 1 to k, what does it mean to have I to the k?
Yes, yes, that's a good question. So I to k is like this is a closed loop. So like if you select, let's say, this bracket, this is like a closed loop, and the product of this edge times this edge times this edge times this edge will be identity. So, but you can, for example, take a larger loop composed of two faces.
Yeah, but is it the same I?
No, this is the imaginary unit. This is
Okay.
the imaginary unit, yes.
Now you can see why I looked at that and went, okay.
Yeah, sorry. So sorry
Okay.
for
Okay,
abusing
so
notation.
not the same I.
Yes. Okay, so we've got our encoding. So now we only need to say what sort of annealing protocol is beneficial for encoding or solving this sort of problems. And from adiabatic theorem, we know that if we evolve slowly enough, we will end up in the ground state. But here comes the catch in these systems. So like our encoded Hamiltonian, because it's living in a larger Hilbert space, doesn't have the ground state that is a logical state. So if we were to, do some thermalization on the physical qubits, we'll end up in a state that is not the true ground state of our problem, but some sort of non-logical state that we don't know fully how to interpret. So we'll need to solve somehow this problem, how to benefit from this encoding. Maybe there is some way of benefiting from the fact that this is not the ground state of the physical qubit, but only the ground state of the logical. So in order to create the protocol, we'll need to select drivers and schedules, A and B functions, and then we'll talk about some initial state preparation and measurement, how to measure this and how to initialize our system. So first, the drivers. So we explored a couple of different possibilities, but it seems that the most beneficial driver for our simulation is a driver that we call a checkerboard pattern that is local in, so like there are two possibilities, local in Z plus non-local with some notion of stabilizers. So in the local case, there are no, the evolution on the auxiliary qubits is trivial. This is identity evolution. And the drivers are composed in such a way that we fix the number of particles. So for example, we want to solve the Fermi-Hubbard problem with 4 particles in this case. So we need to initialize our system with 4 particles. And we initialize them in this checkerboard pattern that this is like 1 excitation and all 4 excitations here. The nice part of that driver is that it commutes with the stabilizers, and also it commutes with the number of particles operator, but it doesn't commute with the full Hamiltonian, so we don't have the trivial dynamics here. These commutations means that we preserve logical subspace. So like if we start in the initial state that is a logical state, at the end of the evolution, provided that the evolution is fully coherent, we will end up in the logical ground state. So we don't have this possibility of ending up in the true ground state that is lower in energy, but we are ending up in the logical state. And on top, if we fix the number of particles, we know that we will not leak out from the number of particle sector here. And if we additionally consider non-local terms, these considerations are also satisfied. So we guarantee that our driver preserves the structure of the problem. And this is why I said that how can we benefit from that encoding. So we are reducing actually the Hilbert space that we are exploring only to the logical and only to the particular sector of numbers, particle number here. Then the state preparation. As I mentioned, here will be exciting, like injecting a number of particles that is related to how many particles we want. So like these are in this case 4, S means that square. and 0 will be on white, so there are no particles here. And then there is like what sort of a state we need on the auxiliary qubits in order that this initial state is true logical state. And this unfortunately needs to be highly entangled, like as a state corresponding to the stabilizer, state that is entangled and requires some extra state preparation procedure. But the good part is that once we initialize it in that state, because the auxiliary qubits undergo trivial evolution, we don't need to manipulate this entangled state. We don't need any special high-level, high-order local interactions. So like our driver is only one local in the evolution, which is also from the perspective of implementation very neat and easy to perform. In our case, we consider the trivial linear schedule, but also we looked at D-wave schedules with, so like I will focus mainly on these results, but also the same conclusions actually hold if we use more elaborated schedule. Finally, the measurement protocol, and the measurement protocol here will be composed of, since our Hamiltonian is non-classical, so we need to go beyond standard Z measurement. So in order to extract the expectation value, we'll need to measure extra, like in total 5 Hamiltonians, 4 non-trivial Hamiltonians, and all Z's. So like the non-trivial Hamiltonians will be that we are measuring, let's say, the blue ones simultaneously, so like in XX, for example, the yellow one, like I don't remember precisely, but like some combination of double X, Y, double Y, Y, and so on. So like the combination of Pauli, all Pauli strings, in total 5 measurements, and that will allow us to then combine them on a classical computer and extract the expectation value. So let's go now to the results, and this is first for the spinless case, and since these problems are already enough complicated that you cannot do too many analytical investigations here, we mostly employ numerical analysis, and we scan different lattices, only restricting to the rectangular lattices, where we were growing the system size up to, for the spinless, 6x6, and looked at the performance of our annealing protocol with total time equal to 100 units, and TV, the parameters of that Hamiltonian being 1, where we looked here at this plot at the difference of the final state after the evolution and the difference with the true ground state. And here I'm comparing, the orange one is fully local without this extra stabilizers terms in the driver, and all means that we also have driver terms in the driver that are non-local. So this shows that in general you don't need to introduce non-local terms in drivers, so you can restrict purely to the local drivers, meaning that the hardware components will be easier because it's way easier to implement purely local terms. The black bars are the minimum and the maximum over different configuration of the driver. So like if we consider, so maybe I will go here. So like if we consider like 4x4 case with 4 particles, obviously this is not a unique distribution of 4 particles on that grid. So we have scanned all possible configurations. So for example, we could have particle here, 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 and here, which is different than that one. And the bars are representing the best driver and the worst driver, and these are the mean values over average over all possibilities. So here we also focus on like looking only at the best performing driver, and one comparing them with the auxiliary and without the auxiliary qubit, so without the non-local terms, just to check if the best performing driver is like performing relatively the same on the scale as the non-local one, but also to check if there is some information about the gaps, and particularly here, like what is the scaling of that. So one would expect that with increasing size, the gap should close, and like the evolution should be longer, and therefore the entire implementation more complicated. But from that part, we don't see particular scaling of the gap, at least up to these systems that are fairly small, but at least promising that maybe extrapolating this could indicate some nice performance on larger scale. And in the case of spinful problems, here are 4x3 lattices where we additionally change the u and t parameter, or actually we keep t fixed to 1 and we change u, and this is a proxy also figure for how difficult it is to simulate it classically. And unfortunately, so we've got like two also different possibilities, since our spinful model will be composed of two lattices parallel to each other. We'll have possibility of initializing our lattice that there is double occupancy on, like if we fix the number of particles, there is a double occupancy, or there is no double occupancy of particles on a given site. And the matching means that there is a double occupancy, and different that means that there is no double occupancy here. And we see that there is like some drop in performance when we get this double occupancy. Here also there is some drop, so like this is something that we would like to avoid. We don't want to see that our fidelity is going to 0, and like we are observing some bad energies. And in order to first understand why this is happening, so like if you've got high U, it means that the on-site interaction is kind of dominating over the coping terms, and on-site interaction is given only by Z operators. It's like the on-site Z interactions, meaning that this term will commute with the driver Hamiltonian, meaning that we don't have evolution or a trivial evolution acquiring phase mostly, with some small contribution of that. So in order to remedy this problem, we additionally introduced some two local terms to our Hamiltonian that also satisfy the commutation relationship, and this brings non-trivial commutativity with this term, and also boosts the fidelity of observing the final state by some amount, which is super promising. Additionally, we looked at some other properties like different observables, local and non-local. So like this will be a local observable, this will be a correlation of non-local observable, and also we observe some good results. And why I'm mentioning this is that in near-term approaches like VQE, people use energy, expectation value of the Hamiltonian energy as the key figure of merit for the optimization. So like you're optimizing the energy, getting in energy landscape close to your ground state, but not necessarily getting a good state in terms of other observables. Here we are keeping our evolution close to the ground state, meaning that we are also preserving other observables, properties of other observables close to the ground state, which is like a nice property, I would say. Additionally, we looked at the gap, like how does the gap change with respect to the final Hamiltonian, so like the final or like pure problem Hamiltonian gap, spectral gap of the Hamiltonian. And what we observe is that the gap is getting to the level of at the very end of the evolution, meaning that we don't have during the evolution some closing of the gap, but the gap is gradually getting closer and closer to reach the minimal value at the end of evolution, close of the same value as the spectral gap, which also might be promising from the implementation perspective that so some sort of analysis on the gap will be related to the analysis of the spectrum of the problem Hamiltonian. Additionally, we looked at noise properties and this is a big simplification to what one would expect from a real hardware. Namely, we looked only at noise present in the T and U parameters. So if we, this is a standard disorder model with the like Gaussian distribution around the perfect values with some standard deviation sigma that is given here with respect to the spectral gap. So like if the noise is, if the standard deviation is like on the order of the gap, we start observing, like some deterioration of the effects of observing the ground state. But not so bad, I would say, that, like having standard deviation, like broadness of your distribution with twice the gap, we drop in fidelity to 92% from like close to 100%. And energy is also not so bad with respect to the ground state. Why I mentioned that this is like super simplification, because this noise model preserves all logical and number of particle structure. So this noise doesn't induce any leakage to non-logical space or outside of the number of particle sector. Yes, so these results, I would say, are kind of promising, but now let's check like how it compares to some other quantum computing approaches or near-term quantum computing approaches for Fermi-Hubbard models. And the comparison that we used here was with probably the largest Fermi-Hubbard simulation on a hardware by Google and Spacecraft, recently published in Nature Communication. And the other was purely theoretical investigation of resources with the VQE variation of quantum eigensolver approach. And in our case, we assumed numbers from D-wave on the annealing, on the other like reset time and so on, like just to have some sort of tangible understanding of what we could expect if this hypothetical hardware is built. Obviously, these, like if we were to build them, these numbers do not have to be the same. But the bottom line here is that it is comparable, let's say, in the total time required for simulation. In the experiments, they consider only 2x4 lattice. In this resource theoretical paper, it was a 5x5 lattice. Also slightly different scenarios in terms of strategy of measurement. Google and Spacecraft did full optimization in like 5,000 seconds, where they collected, during the optimization, they collected only 1,000 outcomes, 1,000 bit strings, averaged them, and used them for the optimization. And the final step was done with 100,000 shots. While in the resource paper, all samples were with 10,000 times 4. And we use the same number because of the structure of the problem. Also, these papers were using Jordan-Wiener transformation, which is different than our. But what is worth mentioning is that this is extremely size dependent. So, like if you were to go to higher lattices, likely in the VQE scenario you will use more layers, more parameters. So, like the classical optimization will be more complex. the circuit execution time will be longer, and so on. While in our case, these numbers are fairly fixed. Yeah, like we can, provided that we've got access to that sort of device, we can increase the size and simulate them at one go, and there is no issue with that. And finally, what are the perspectives for implementing this? And yes, so far we've been using mainly these sort of interactions, so like local transverse field, local Z fields, and ZZ interactions, either in the driver or in the problem Hamiltonian. But in our proposal, we require way more complicated components, and in particular, our Hamiltonian is not classical, so we need to go beyond that. However, there are some endeavors on creating ZZZ or four-way Z couplers in order to also implement some combinatorial problems, which might be promising for maybe changing them somehow to implement other Pauli operators. And one of the potential candidates that can achieve that is just some facelift qubit that gives us possibility of implementing XXY, YYY, and so on. However, this is like in very preliminary stage of research, so it's not decisive that this is the technology that we have to invest in order to build that device. Additionally, this qubits could be beneficial also for implementing the measurement scheme where you require XYZ measurements and not only the Z-type measurement, which also brings us to some sort of additional point that so far we've been only looking at the classical problems, and therefore we were not interested even in investigating measurement schemes that were not in Z basis. Yeah, and finally, to conclude this, I guess that I presented here a proposal supported by the numerical results that maybe it's a nice alternative pursuit for solving Fermi-Hubbard models with novel type paradigm to annealing. However, there are plenty of challenges, especially noise. If we consider leaking noise, decoherence, that we are leaking from the logical subspace to non-logical subspace, how to kick us back to the logical, or how to mitigate these effects. State preparation, as I mentioned, like we need to prepare this entangled state on the auxiliary qubits. There are efficient ways of preparing these states in the gate-based computer, but we couldn't figure out precisely how we would like to prepare it in the annealing scenario. Then obviously scaling analysis, like we can only say what we observe in low dimensional systems through numerics, but this doesn't guarantee that going way higher it will be the same. And finally, like, is it worth even pursuing experimentally this? And if we start doing this, like, what are the perils there? And thank you for your attention.
Questions? Let's go.
Thank you for the talk. I have a question. You mentioned that the noise that you had been looking into still respected the Have you looked into, or are you planning on looking into the effect of noise?
Yeah. So in general, yes, we plan to consider some other noise, especially more from adiabatic master equation perspective, like implementing some sort of still coherent noise that is leaking is, I'd say, like hand waving in the sense of like justifying why this sort of noise would appear. So like one possibility of implementing coherent leaking noise would be that you add arbitrarily some term to your Hamiltonian that is breaking the symmetry with like some properties. But then the question, what sort of term and why this term and not the other one? The other possibility would be, instead of like implementing x that can be, like given by the exponent of the Pauli matrix with appropriate phase. This phase is close to pi half and is fluctuating. But this in general, as well as the adiabatic master equation, brings additional problem of limiting simulations to very small systems. So in our simulation, we could exploit the fact that we are only exploring this logical subspace and the number of particles. Therefore, we could go even to 6 by 6 for spinless particles and 4 by 3 for spinful particles. If we were to consider full Hilbert space and also density matrices as in the decoherent noise, our simulation will be restricted to smaller systems. So like there needs to be some sort of additional innovation of how to manipulate with the data in an efficient way in order to include some decoherent effects and still be able to go to decently good system sizes.
Thanks, Philip. Very nice talk. Maybe my question is unfair. I don't know. But, clearly, everything in this field so far is on a two-dimensional lattice. Most superconductors I work with in the lab are three-dimensional. What are the challenges in going to 3 dimensions, both in terms of your local weight reduction, which maybe is very different, and also then how you might implement it on an annealer, for example?
Yeah, so the main, I would say, the starting point for even doing this analysis will be, so like the encoding that we employed here is given for 2D lattices. So I'm not aware of this low weight encoding happening in 3D, and this might already bring us to higher Pauli weights, which will be, like extra degree of freedom in the complexity. And I guess that this is already what the starting point is the problem. So like I don't know what to expect even going further.
I have a similar question about the model of Fermi-Hubbard. Actually, you are now considering the on-site Coulomb interaction and the nearest neighborhood, right?
Yes.
And if we want to go beyond, for instance, the nearest neighbor Coulomb interaction or the second nearest neighbor or something, in this case, that the mapped system also still there kind of the similar two-dimensional lattice model still.
Yeah. So the encoding that I introduced here is was investigated based on nearest neighbors interactions.
Yes.
And this is why you can introduce these directional edges. I don't think that there is a paper doing, at least in this low weight encoding, next nearest, for example. And that's a very good question, because next nearest neighbors is more promising, like harder to investigate, simulate. And from that perspective, it'd be even better, more promising if we were to have a simulator of that, like an analog quantum simulator. Maybe quantum advantage would be easier achievable there. But the issue is the same as with the 3D. We don't have precisely way of encoding, and this also kind of indicates that I'd say that there is like importance in investigating different encodings and trying to find an efficient encoding, and also maybe an encoding that is tailored for your problem, because also we could consider, so like in general, let's say if you get a superconducting qubit, you don't need to restrict yourself only to the computational basis. You might use, let's say, a second excited state as some sort of mediator of the computation relationship. So like there is some need for looking at these encodings from that perspective and maybe doing something hardware efficient in order to implement more complex problems.
Okay, very interesting. Yes, thank you.
Do we have more questions? If not, we're on perfect timing. Let's thank Filip again.